So welcome to day 2 of ADMA. It's day 2 is devoted to cryptography. So we have a bunch of talks related to cryptography and some on mathematical aspects related to cryptography. So we are going to begin the session with talk by Professor Sudhir Ghorpade, who's with Mathematics Department at IIT Bombay.
Okay, can you hear me? So good morning everyone, and sorry maybe you had to wait a few minutes. So as the chair said that this session is about cryptography and as he put it, mathematical aspects of cryptography. And so when I was to come for this conference, I was actually supposed to speak in another session, which was yesterday on coding theory. So if you have the booklet of abstract, I proposed a talk on a topic in coding theory which has been of current interest to me. And when I realized some 2 days before the conference that my talk is moved to the cryptography session, so I thought I should also make a move myself a little bit. So I decided to change the topic and say something which is related to cryptography, so that people in this session don't throw me out or something like that. And this is somewhat older work, and maybe some of you have heard this. On the other hand, I think there are still some nice problems for people to look at, although the work is kind of carried forward by my former students and other colleagues and so on. So as the title says, I'm going to talk about some type of recurrences, objects known as single cycles, which are you could say something in group theory, and splitting subspaces, which is if you like a notion in linear algebra or finite fields. Okay, and I'll define what these are. I'm going to start with something that I think every cryptography expert would know about, which is what are called LFSRs. LFSRs, which is just a shorthand for linear feedback shift register. And it's, that's the popular parlance. In mathematics, we would call it a linear recurrence or homogeneous linear recurrence. So what is a LFSR? So here is the definition. So you sort of start with some constants C0, C1, Cn minus 1, and some kind of another bunch of initial constants, n constant, S0, S1, Sn minus 1. And then you use that to generate infinite sequence as follows. So you have C0, C1, Cn minus 1, S0, S1, Sn minus 1. You look at S0, C0 plus S1, C1 plus Sn minus 1, Cn minus 1. That linear combination, that is Sn. Having gotten yourself a Sn, you shift, because as the name says, shift register, you push this S0, S1, Sn minus 1 to S1, S2, Sn. And then again now stick with C0 S1 or S1 C0 plus S2 C1 and Sn Cn minus 1 and so on. So the general definition is here. So LFSR of order n over the finite field, Fq is the standard notation for finite field with q elements, is simply this recurrence relation which is corresponding to these constants. C0, C1, Cn minus 1 and what is called the initial state. Another way to codify these constants is by writing a polynomial of degree n, and I prefer to write it like this: x to the power n minus Cn minus 1, x to the n minus 1 and so on up to minus C0. So giving this polynomial is same thing as giving this constant, and this is called the characteristic polynomial of this LFSR. Okay. So it is obvious, I mean more or less that's how the definition is built in. Cryptography books will have this kind of diagram which will show you how you feed things and move one step and you get this. So very classical things. So such a thing you see, you have such a recurrence relation, so you start with this data and it will obviously generate an infinite sequence of elements of Fq for you. S0, S1, Sn, Sn plus 1 and so on. Okay. And the way it is typically used is that, okay, I mean sort of idea is that if you choose your C0 to Cn minus 1 cleverly, so that you start with some n tuple and you are able to generate an infinite tuple which is sort of as random as it gets. Okay. This randomness is a concept which is somewhat curious, because moment you write something down, it is not random. So, maybe the technical thing is pseudo random and so on. So, and one way you can use it is what are called stream ciphers, which I think everybody knows. So, let us say you want to send your credit card number, it is a big number and you do not feel comfortable in sending it. One simple thing you could do is you take that long vector, you add to it some randomly generated vector. Let us say you are in the binary field. Okay. So, then of course, the coordinates get changed. You send that across, and even if a person were to hack it, he would not quite know the original number, and the person receiving it, all he has to do is to again add that randomly generated thing, and then you get back your message. So, it is sort of useful that you can generate sequences which are sufficiently random in some structured way. Okay. So, very good. Of course, you are over a finite alphabet set, finite field. So, such a sequence will in fact necessarily be periodic or rather ultimately periodic. What does that mean? That means after some stage, blocks will just repeat themselves. Okay. So, that means there exists a positive integer r, and that r is in fact at most q to the power n minus 1, such that Si plus r is Si, maybe not for all I bigger equal 0, but for all I after some stage, say bigger equal n 0. So, the least positive such r is called the period of this infinite sequence, and for that period the least non-negative n naught is sometimes called the pre-period. Okay. It is also a general fact that the sequence is sort of periodic, or you might say purely periodic, which means that you can take pre-period to be 0 if the number C0 is non-zero. Okay. And the important basic definition here is what is called a primitive LFSR, or a primitive linear recurrence. What does that mean? That means, it means that no matter what initial state you take other than all 0, because if you take all 0, then of course sequence you will get will be all 0. The resulting infinite sequence should be periodic of maximum possible period, of period q to the power n minus 1. Okay. So, obviously, this is sort of the limit of randomness that you can generate out of this basic data and this simple procedure. Okay. So, I repeat, the LFSR or this homogeneous linear recurrence is said to be primitive if the resulting infinite sequence is periodic with period q to the power n minus 1 for any choice of non-zero initial state. So, primitive LFSR is an object which just depends on those numbers C0, C1, Cn minus 1. You feed in any initial state, not all 0, then the resulting sequence should be periodic of maximum possible period. And it is these primitive LFSRs which are of basic interest. A natural question would be, what is the number of primitive LFSRs of order n over the finite field? Okay. So, this is a classical thing and it has a well known answer. So, to explain that, I want to by the way, the word primitive is a word which occurs in many parts of mathematics. In calculus, sometimes primitive is another name for antiderivative. In elementary, when you study complex numbers, you talk about primitive nth root of unity, or primitive, or maybe in a group theory you talk about primitive element of a cyclic group. This primitive nth root of unity, primitive element of a cyclic group is more or less the same thing. Primitive, if you have a cyclic group, a generator of that would be called a primitive element. So, primitive nth root of unity is a generator of the cyclic group of nth roots of unity, which is a cyclic group of order n, right, the division points on the circle. A primitive root modulo n, which is a generator of the group Z mod and Z cross in the situation when that group is cyclic, and you know from elementary number theory when it is cyclic. So, what is the connection with that sort of primitive with this primitive? Well, that comes from algebra. It is a classical fact that a LFSR of order n is primitive if and only if its characteristic polynomial, remember I wrote it down, this is the characteristic polynomial, this is obviously a monic polynomial, coefficients in FQ, is what is called a primitive polynomial of degree n. What is a primitive polynomial? For those of you comfortable with algebra, I can give a one line definition. I have the finite field FQ, then I can construct a bigger field with q to the power n elements. From the point of view of field theory, this is a field extension of degree n. You look at the non-zero elements of that, say this, that is a cyclic group. So, maybe it is generated by some element sigma. You take any generator, in other words, you take a primitive element of this multiplicative group of non-zero elements. Now, this is a group element in this field, you take the minimal polynomial of this element sigma over FQ. Okay. Sigma will obviously also generate this field as a as a this. So, this is a monic polynomial. So, this is a polynomial with coefficients in the ground field, monic of degree n, monic irreducible of degree n, but it is little bit more than irreducible. So, primitive polynomial is always irreducible, but an irreducible polynomial need not be primitive. Why? Because it may not, it may not be, it could be a root of something which is not a generator of this group. After all, this set contains lots of element which do not generate it, but which may generate it as a field. That is to say, FQ to the n is FQ parenthesis sigma. Okay. There is another way of defining it, which is you can call define what is called the order of a polynomial. See, there is a finite field is a nice interesting things, because what happens is that when you are in a finite field, everybody, well, almost everybody, that is to say everybody other than 0 is a root of unity. Why? Because anything other than 0 is in the multiplicative group, which is as finite order. So, you raise it to a sufficiently high power, it is a root of unity. You can, in principle, you can use this to sort of observe that if you take a polynomial fx of which 0 is not a root, which means every root is a root of unity, then that polynomial has to divide something like x to the power e minus 1, this so called binomial. Okay? And when you observe that, then you can take the least e for which it divides x to the power e minus 1, that is called the order of the polynomial, and the order of the polynomial will be a number which will be between 1 and q to the power n minus 1, and the polynomial is primitive if and only if the order is q to the power n minus 1. Okay? So, that is another definition of primitive polynomial. A primitive polynomial is a monic polynomial of degree n whose order is this, and which has this property. Okay. So, now you see, once you understand this connection, it is very easy to write answer this question, the number of primitive LFSRs of degree n. How do you do that? You have this group here, this guy has q to the n elements, this is q to the n minus 1, cyclic group of order q to the n minus 1. How many generators this has? That is phi of q to the n minus 1, the standard thing. So, the number of possible generators, possible sigmas will be phi of q to the n minus 1, but now you are not counting generators, but you are counting polynomials, a polynomial of degree n like that. So, polynomial of degree n will typically have n roots. Okay. So, if you are counting polynomials, you have to divide by n. By the way, those of you who like elementary number theory could sort of take this as an elementary exercise to show that n always divides phi of q to the power n minus 1. You do not need notion of primitive polynomial for that, but anyway. So, that is sort of easy aspect, that phi of q to the power n minus 1 upon n is the number of primitive LFSRs. Okay. So, this is a good number. All right. So, there is another word in the title of my talk called Singer cycle. So, maybe I will explain this. So, what are Singer cycles? So, I look at what is called the general linear group, which in the classical setting is what Hermann Weyl called her all embracing majesty in a famous book called Classical Groups, which is just a set of all non-singular n cross n matrices. In this case, I am going to take it with entries in FQ. what happens with the entries are in FQ, then this becomes a finite group. Usually when entries are in R or C or whatever, it's an infinite group. But here it's a finite group and its order is very easy to figure out. You want to count the number of non-singular n cross n matrices. Yeah. So you have your n cross n matrix that has q to the power n possible entries, but then you want it determinant to be non-zero. So the first row should not be 0. First row you can choose in q to the n minus 1 ways, and you forget the 0, so q to the n minus 1. The second row should not be a multiple of the first, so you subtract all the q multiples of the first one, q to the n minus q. Third row should not be a linear combination of the first two, so that is q square. So then q to the n minus q square and so on. Nth row should not be a linear combination of the first n minus 1, so that is q to the n minus q. So it is an elementary exercise which we just solved, that the order of this finite group is this. Natural question, now that it is a finite group, this is a more interesting question. Every element has a finite order. So what is the maximum possible order that an element in this group can have? And this has a nice answer. Obviously you do not expect maximum possible order to be the full order, that would make the group to be cyclic. This group is not even abelian unless n is 1. So before I tell you, let me throw in a word. So the Singer cycle is an element of GLNFQ which has a maximum possible order. Now what is that maximum possible order? Well, and how is it related to what I just said? Here is the relation. So this is mixing group theory and linear algebra. You take a n cross n matrix with entries in FQ, then you can associate to it some natural monic polynomials. One is called the characteristic polynomial, which is a monic polynomial of degree n, and another is a minimal polynomial which can have degree smaller than n, so it is less equal n. And it is a general fact which you can prove as an exercise that this matrix is a Singer cycle, it has maximum possible order if and only if this characteristic polynomial, which is now a monic polynomial of degree n, coefficients in FQ, is a primitive polynomial in the sense that I defined a minute ago. Okay? In fact, you can say a little bit more general, that the order of the element A is precisely the order of the minimal polynomial in the sense of order that I defined a minute ago. I defined. So once you have that, and if you believe what I told you, that the order of a polynomial which as you can see from this definition and so on does not exceed q to the power n minus 1, I have an answer to this question, that the maximum possible order that an element of GLNFQ can have is q to the power n minus 1. So max of orders of element. So in other words, a Singer cycle is an element in GLNFQ of order q to the power n minus 1. Okay? And you can these Singer cycles were introduced by a American mathematician whose last name is Singer, but many of you might know a famous mathematician called I. M. Singer. This is I am not Singer, in the sense he is James Singer, who wrote a paper in Transactions in the 30s which had to do with projective geometry, but really people have later on found this very useful in group theory. So good groups on group theory will have notion of Singer cycles, but unfortunately the number of those books is rather small. You can ask me. All right. So this Singer cycle, so for example that cyclic subgroups of GL and FQ generated by Singer cycles are called Singer subgroups, and they have some nice properties, some kind of properties similar to Sylow subgroup. Any two Singer subgroups are conjugates of each other, for instance. So anyway, you can use such a little bit of group theory to not only answer how many elements, what is the maximum possible order, but how many elements of this group have that maximum order. And that answer will again involve the number that you saw a minute ago. It is this number of primitive LFSRs times what looks almost like the order of GL and FQ, but not quite. It is order of GL and FQ divided by q to the power n minus 1. That first term is not there. You start with q. So, okay. It's not very difficult to show, but does need a small amount of proof. All right. This is all really, at least the previous slide, it's very classical and standard, and I think I just wanted to say it, although every cryptographer would probably know about it. This is slightly less known, but still very classical. What the problem that we were interested in, or I became interested in, I can tell you the story later on, is the following. is a natural generalization of this notion of LFSR. So, what is that? You take instead of taking constants C0, C1, Cn minus 1, you take matrices, m cross m matrices, say capital C0, C1, Cn minus 1. And instead of your initial state being also elements of Fq, you take them to be vectors. So, you take them to be, say for example, m tuples of elements of Fq, Fq to the power m. The nice thing about finite fields is that you can move at m. So, Fq to the power m in the sense of vector space is naturally isomorphic to Fq to the power m. So, unlike real numbers, finite dimensional vector spaces over finite fields have a natural multiplication structure, which as I sometimes say, just gotten by moving m from there to there. Okay. So, you could think of these SI, now I have made them boldface, as something sitting inside this. Capital Ci's are m cross m matrices. So, I am thinking by the way of my vectors as a row vectors, which is kind of standard in cryptography. In mathematics courses, I would be thinking of them mostly as column vectors and write it on the right, but here I am thinking of them as a row vector. So, therefore, this is a 1 cross m multiplied by m cross m, that is 1 cross m vector again, and you have the same recurrence relation, okay, for all I going from 0, 1, 2 up to n. So, so you can, so this is the initial state which is a n tuple, but whose elements are vectors, and obviously such a matrix recurrence, if you like, will give rise to an infinite sequence of vectors S0, S1, etc. And you can prove that that sequence is also ultimately periodic. That means eventually it gets blocks get repeated, and the period in fact is maximum possible period. I think I have not written it down here, is q to the power mn minus 1. Okay. So, there is a m and n are always positive integers, and one can of course define the same way the notion of primitive vector recurrence or primitive. By the way, these are vector recurrence, another word for it is sigma LFSR. So, you can call them a primitive sigma LFSR. What is a primitive sigma LFSR? A primitive sigma LFSR is that choice of n tuple or of these n matrices C0 to Cn minus 1, such that for every non-zero initial state in here, the resulting sequence is primitive of maximum possible period, namely this. Okay. And earlier remember we had that that sequence is periodic if the C naught is not equal to 0. Here now C naught is a matrix, the analog of that is the sequence is periodic if C naught is a non-singular matrix, determinant non-zero. Okay. Now, here is a nice problem which is determine now the number of primitive vector recurrences of order n over the field or over the vector space Fq to the power m, or as I said equivalently over this field. It turns out that this is a much harder problem. Okay. And problem difficulty is because, okay, well, like before you can write down the characteristic polynomial. It will be a polynomial which would look like this, but this is a polynomial in monic polynomial of degree n whose entries are in the non-commutative ring of matrices. So, there is no way you can expect it to be a minimal polynomial of some element of a field extension and so on. Okay. So, you cannot really realize it as a minimal polynomial, and so you cannot kind of do the sort of trick you did in the classical LFSR. If you really insist on a characterization, you do have a characterization, and it is the following. What you do is you take your matrix, say Lth matrix, you write the ijth entries, then for each ij you can write down now the polynomial which is a polynomial with coefficients in Fq. Okay. So, in this way I get m square polynomials for each I and j between 1 and m. I put those m square polynomials as a m cross m matrix. So, this is a matrix, each entry of which is a polynomial of degree n coefficients in Fq. You take that big matrix of polynomials, take its determinant, that will be a polynomial, a monic polynomial over Fq of degree mn, and it is a fact that the vector recurrence is primitive if and only if this big polynomial is primitive polynomial. Okay. And is there a connection to Singer cycle? Yes, I will explain that. and there is also connection to other topic that is there in the title of sigma splitting, which also I will explain. So, so these vector recurrences have a funny history, because when I learned about them from my PhD student who was in DRDO and working with his boss at the time, he showed me a paper by these Chinese mathematicians Zheng, Han and He in eCrypt archive, and they looked at this sigma LFSR over binary case, and they seemed obviously very excited about this idea, and they did various things, except that some years later I realized that what they did in 2008 was actually done by Niederreiter way back in 1993. He called it vector recurrences, they called it sigma LFSR. But this Chinese people had something interesting. Oh, and by the way, they only worked over q equal to 2, that is of classical interest, a binary case. In the binary case, they made a conjecture that the number of primitive vector recurrences of order n over f, which is essentially says like that, at least they did it for q equal to 2, is given by this formula, this remarkable formula. You recognize the first factor here, that would be the number of linear recurrences of order mn, primitive linear recurrences of primitive LFSRs of order mn. But it is not just this, there is a big power of q and there is GLM divided by q to the m minus 1. So, what that means, see that makes the eyes of cryptographer light up, because what that means is, instead of doing this roundabout way of taking matrix and so on and so forth, I could have just worked with the field fq to the mn and looked at LFSR there. What is the advantage of doing this? Well, the advantage of doing this, if you did that, then the number of primitive ones would be just this much, whereas if you did the sigma LFSR, it is much larger. So, there are more possibilities, therefore less probability that things can be hacked and so on. So, as you know, this is apparently a solution to a problem proposed by Bart Preneel of designing this stream cipher, which takes into account parallelism and things like so-called word-oriented stuff. Okay. Anyway, what I got interested in was by this formula, which is such a beautiful looking formula. I like formulas. So, we started thinking about it. So then I wanted to translate it to group theory. So, that is not so difficult. So, by the way, it is a classical fact from linear algebra. If you are given a monic polynomial, is it always the characteristic polynomial of some matrix? Answer is yes. All you do is you write down what is called the companion matrix of that polynomial, and then take its characteristic polynomial, that will be the given monic polynomial. Okay. So, here my characteristic polynomial is a polynomial with matrix entries. So, what I do is I look at a companion matrix, but whose entries are matrices. So, this is what I call a block companion matrix. Companion matrix, typically you have zeros and you sort of put the coefficients of the polynomial in the end as a column, last column. Okay. So, here now I am going to put those m cross m matrices here, C0, C1, Cn minus 1. Then I will have in the first row all the previous entries to be m cross m matrices, all of whose entries are 0, and then I will have this diagonal of this block. I will put the m cross m identity matrix, and everywhere else I put 0. It is just like a companion matrix, except the entries are blocks, entries are m cross m. So, that is why I call it a m comma n block companion matrix. So, that is just a matrix of this form, okay, where C0, C1, Cn minus 1 is there. By the way, although this looks horrendous, so this is really a mn cross mn matrix. What is its determinant? That is kind of easy to see, because the only sort of term in the block thing it will survive is you have this identity and you have the C0. So, determinant of this will be plus or minus determinant of C0. In other words, this will be non-singular if C0 is non-singular. Okay. All right. So, so when it is non-singular, it is a element of GL MNFQ. Okay. So, I will call this block companion matrix to be a block companion Singer cycle if that matrix is a Singer cycle, which means it has the maximum possible order in GL MNFQ. Okay. Very good. That is q to the mn minus 1. So, that is, and the problem that I asked you, the number n, capital N m comma n q, which is the number of primitive vector recurrences, which was conjectured to be this. turns out this number is same as the number of Mn block companion Singer cycle. So, you could be talking about primitive vector recurrences, or you could be talking about block companion Singer cycle. They are one and the same thing, because very good. So, but then it is not so easy. Okay, so now maybe I should explain what are splitting subspaces. So, splitting subspaces is a concept which actually originated in Niederreiter's paper. He pointed out that these are relevant for his vector recurrences. What is a splitting subspace? I told you already that if you are in a field over finite field, so if I look at say this Mn dimensional vector space, it has a natural multiplication. So, if I take some element sigma here, and if I take some subspace W, say W of dimension M, okay, then I can form a new subspaces. I can take W, I can take sigma W, and so on, sigma to the power n minus 1 W. It's the kind of thing you do not do usually in linear algebra, because there is no multiplication, but here I do have a multiplication, and so each of them will be an m dimensional vector space, and we will call this W to be sigma splitting if all of them are essentially disjoint and their direct sum is the full Mn dimensional vector space Fq to the Mn. Okay, that is the definition written there. So, W, an m dimensional subspace of Fq to the Mn is called sigma splitting if this happens. And Niederreiter, the question that he asked in his 95 paper is that given an element sigma with this property, actually he assumed more, he assumed sigma to be a generator of the multiplicative cyclic group, which implies this, and he actually assumed q to be a prime number, but I have just made the question a little bit more general. What is the number of sigma splitting subspaces of Fq to the Mn of dimension m? Sort of innocuously wrote that this is an open question, which kind of remained open for almost 15 years, and of course, there is a trivial way in which you can solve just about every question, namely just give a name to this number, I call it this, and say, oh, the answer is this, but that's not very intelligent. What you would like is some kind of a formula for this, and but before, let me at least remark that if for an arbitrary sigma, there may not be any sigma splitting subspace. Why? Because suppose I take sigma to be in Fq itself, okay, then that means it is a scalar. So, if I multiply this W by that scalar, I am not going to get a different subspace, all of them are W, okay. So, they are not going to add up to give you the full space unless n is 1, okay. So, on the other hand, if sigma does satisfy this condition, then you are assured of the existence of at least one sigma splitting subspace. For example, this, because if this happens, this means 1 sigma, sigma square, sigma to the Mn minus 1 is a Fq basis of this field. So, but then you just take 1, you jump to sigma to the n, you jump to sigma to the 2n, and so on, and then you sort of multiply them by 1 sigma, sigma to the n minus 1, then you will see that you will get the whole space, okay. So, this condition ensures the existence of at least one sigma splitting subspace. It does not tell you what are all possible, okay. So, let me just, so what we did was, so the first steps towards a solution. How much time do I have? 15 minutes, wonderful. So, as with my former student Sartaj and his boss Meena Kumari in DRDO, we wrote a paper in this design course cryptography in 2011, so it is already some time, and where we kind of proposed how you might go about doing this. So, what I thought was the natural way to sort of think about this, I want to count, for example, these block companion Singer cycles. When is so that means I want to count such block companion matrices whose characteristic polynomial is a primitive polynomial. Now, there is a natural map going from the set of matrices to set of polynomials, namely the map which takes a polynomial to matrix to its characteristic polynomial. So, I look at this characteristic map as it were, just sends a matrix T to its characteristic polynomial, and so what we observed, and then I can restrict it here to Mn block companion Singer cycles. Then if that your element of the domain are Singer cycles, the polynomials that you will get will be primitive polynomials, the monic polynomials of degree m. and but of course, it is not obvious that if you are given a monic polynomial of degree mn, which is primitive, it is the characteristic polynomial of some mn block companion Singer cycle. It is surely the characteristic polynomial of some mn cross mn matrix. That means, you take the ordinary companion matrix of that polynomial. But what we want is, we wanted that special block form, whose n cross n, whose block entries are m cross m blocks. So, that is not quite obvious, but we actually showed that that map is surjective, and and then what we thought was a natural way of sort of doing this, because so once you sort of, okay, so here is a, so let me call something block companion Singer cycles, say mn, and then I have a map to primitive polynomials of degree n. So, T going to characteristic polynomial of T. Now, what we showed is that this is surjective. What I am interested is to count this. So, obviously, the cardinality of the domain, maybe let us call this phi or something. Okay. The cardinality of this is summation of the cardinalities of the fiber, where f varies over primitive polynomials of degree mn, right. So, therefore, and I know already what is the cardinality of this, that is the first factor in the conjecture formula, this one. Okay. So, if I can show that the cardinality of each fiber is the remaining factor, which is this, then I am done. Of course, that is much stronger than saying the cardinality of this whole set is that, because maybe the fibers are not sort of equidistributed, and but still somehow they add up to that. But we had reasons to believe that actually a stronger thing is true. So, that is what I call a primitive fiber conjecture, or PFC, which said that for any primitive polynomial of degree mn, the number of mn block companion Singer cycle having that polynomial as the characteristic polynomial is this other factor. Okay. And it is obvious that this will imply the block companion Singer cycle conjecture, and therefore, primitive vector recurrence conjecture, which at least in the binary case is of this Zegan and her. And so, we proved this surjectivity using a little bit of Galois theory and so on. And here this thing is, by the way, obvious if m is equal to 1, in which case this factor is not there, and this product is also not there, because this is an empty product if m is equal to 1. M equal to 1 is just the classical case of LFSR. Okay. On the other hand, if n equal to 1, then this factor is not there, but this factor is still there. So, you still need a slight amount of work to check even if n equal to 1. Okay. So, we proved this this conjecture, and therefore, these two in the special case when n is equal to 1. But then, so that was sort of what is in the paper. We made a query formulation of the problem, showed equivalence to these block companion Singer cycles, showed the surjectivity of the characteristic map, and made this primitive fiber conjecture and proved all of them in a very special case of n equal to 1. And then we wanted to know what is more. So, the next case that we looked at was, okay, so with this now m equal to 1 or n equal to 1 are taken care of. Then you can look at least the next case, which would be that, and the one that we looked at was the case of m equal to 2, which means my blocks inside that matrix are 2 by 2 matrices. Okay. So, this is a joint work with another former student, Samrit Ram, who is in IIIT Delhi now, also published, somehow it got published in the same year, but this was done later. What we showed, we gave another proof that this characteristic map gives a surjection, and we thought not just this primitive fiber conjecture is true, but something more is true. Remember, I told you that a primitive polynomial is irreducible, but a irreducible or a monic irreducible polynomial need not be primitive. On the other hand, this map can be defined at any level. So, I could look at block companion matrices whose characteristic polynomial is irreducible. So, you will get a codomain to be whatever that is, and what we felt was something stronger is true, which is what I call irreducible fiber conjecture, which says that not just primitive, but given any irreducible monic irreducible polynomial of degree mn, The number of mn block companion single cycle having that as its characteristic polynomial is also given by the same quantity, just depends on this q, m and n. Okay? And it turns out, as we realize, that this conjecture, which is a stronger form of primitive fiber conjecture, is closely related to the question that Niederreiter had asked. Niederreiter, remember, asked us what is the number of sigma splitting of subspaces of dimension m. He did not say the number should be this. Usually it is much easier to answer questions when you are told that what is it that you want to prove, but in research we do not have that privilege. Sometimes we do not even know what we want to prove, we just want to get a good formula, we do not know how it looks like. So, at least getting a good guess is sort of half the battle won in some sense, at least that is my experience. Anyway, so, I will explain this connection in a moment. And what I would like to tell you is what we did then is that we proved not just the primitive fiber conjecture, but also this irreducible fiber conjecture in the case of 2 cross 2 blocks. And what I personally find more interesting is one of the things which went into the proof. One of the things that went into the proof, which probably could be of independent interest, there are people in mathematics and so on here, I suppose, and that is so I am going to digress and say a little bit about that. So, what is the question? Before even I show you the slide, the question is like this. Suppose I take polynomial with coefficients in the finite field FQ, say polynomial of degree 100. Okay? I randomly pick up 2 polynomials. What is the probability that these randomly picked polynomials are co-prime, are relatively prime? That means their GCD is 1. Okay? See, remember when I say polynomial in coefficients in FQ of degree 100, let us take monic even, then there are only finitely many, there are q to the power 100. It is a large number, but it is a finite sample space. Okay, I pick 2 guys randomly, I ask what is the chance that they are relatively prime. Okay, it turns out to be a classical question which has been looked at and re-looked at by various people, as we ourselves discovered, and the instance where we found it was in a paper by this combinatorialist Cortil, Sylvia Cortil, Carla Savage, Herb Pentoran, Zeilberger, who were doing some kind of partition theory, and they were, if you know partition theory, there is what is called Euler's pentagonal number sieve and so on, and there they wrote down bunch of generating function, and somehow as a byproduct they observed that the probability that 2 monic polynomials of degree n over FQ randomly chosen are co-prime is 1 minus 1 over q. So, very nice result, which means, for example, you are in a binary field F2, I take polynomials of degree 100 over F2, the probability that they are co-prime is exactly 50%, is half. Okay, there is a 50% chance that the pair that you picked is co-prime, 50% chance that it is not co-prime, and the chance becomes more if your fields are higher. So, it is like 1 minus 1 over q. Okay. And because these are combinatorialists, they said that this is really interesting, and the way combinatorialists like to explain such things is by means of a bijection. For example, you are in a binary field, to really understand that the probability is 50%, they say that we should say that there should be a natural bijection between set of pairs of polynomials which are co-prime and pairs of polynomials which are not co-prime. And so that was given by this mathematician Ralph Jurist pretty soon. Then Benjamin and Bennett looked at the general case, and they sort of gave an explanation for this by looking at the set of co-prime pairs and defining a map of this to non-co-prime pairs, which is a surjection, so that the cardinality of each fiber is q minus 1, and that would explain that this is q minus 1 upon q. Okay, so that was a very nice explanation, essentially better understanding of Euclidean algorithm and so on. But now, by the way, some of you may have seen this other counterpart of this problem, that suppose instead of polynomial I look at integers, you like positive integers. Okay, I pick up 2 positive integers at random. What is the probability that the GCD is 1? I think, does somebody know the answer? If I take m and n positive integers picked randomly, what is the probability that GCD of m and n is 1? Yeah? They are relatively prime, yeah, that is right. So I'm asking what is the probability that Mn in n have GCD 1. This time around it is an infinite sample space. This has a very interesting answer, which if you ask me in the question session, I will explain you why it is true. Probability is 6 over pi square. It's a beautiful little thing. And then, polynomials in one variable and integers are very similar object. This is in fact one of the morals of high school education, because in school we learn about integers till 6th standard. Then a fellow called X enters our curriculum, then we start learning about polynomials. We do the same thing: addition, subtraction, multiplication, division, GCD, LCM. And of course, if you continue to study further, you acquire new names: Euclidean domain, principal ideal domain, unifactorization domain, etc. And all these have the same property. In fact, polynomials in one variable with coefficients in a finite field are even closer to integers, because quotients by non-zero ideals are finite. So at least philosophically, integers and polynomials in one variable should be similar, which means 1 minus 1 over q is something like 6 over pi square. And I wanted to understand that, and I think there is a nice, so if you allow me, I will digress and sort of say that. So the probability of two integers to be co-prime is 6 upon pi square, which is 1 over zeta 2. Zeta is the Riemann zeta function. Okay? So here is a small argument. So there is, that there is a wonderful generalization of Riemann zeta function in the setting of algebraic geometry called weight zeta function. And what it is that you take any variety V over Fq, which means a set of solutions of a bunch of polynomial equation. You take the number of Fq to the n rational points, solutions with coordinates in this, if you like, and you encode that whole data for each n bigger equal n by this exponential generating function. You take this number, multiply, take another variable t to the n upon n, and you have a formal power series without a constant term. You take its exponential, that will be another formal power series, and Andre will argue that this, or rather this, when you substitute q to the power minus s, is very close, very similar, very analogous to Riemann zeta function. And he formulated these so-called Weyl conjectures and so on, which actually have been proven, although Riemann hypothesis is not proven. The Riemann hypothesis in the context of this Weyl zeta function, etc., is proved. And you see the way polynomial ring in one variable corresponds in geometry to the affine line. Okay, so that is just A1, and it is very easy to count how many points there are. Here there are q points. If you are Fq to the n, there are q to the n points. So then your exponential generating function will be this summation and take its exponential. This is familiar to everybody who has taken calculus. This is like log of 1, minus log of 1 minus qt, or log of 1 minus qt inverse. Then you take exponential, so exp and log will cancel each other. So what you will get is 1 minus 1 over qt. So then this is, and I told you that when you substitute q to the minus s for t, that's like the zeta function. So you can now, so if I want to evaluate 2, I substitute q to the minus 2 here, and I can calculate and take its reciprocal, and lo and behold, that's 1 minus 1 over q. So this is sort of a philosophical proof why 1 minus 1 over q is like 6 upon pi square. But I go back to splitting, because I am supposed to, how much? 5 minutes? Okay. In 5 minutes I will finish. So remember, we are talking about splitting subspaces and this question of Niederreiter. So and I gave a name, S sigma mnq is the number of m dimensional sigma splitting subspaces, that means object like that. And this analysis of irreducible and primitive fibers and so on that we did, in fact, led to a quantitative formulation of Niederreiter's question. Niederreiter asked what is this number, and we said, well, this number should be this. And you see, it is not very, it is somewhat similar to what we had before. We still have this power, a big power of q, and we multiplied by this factor, q to the mn minus 1 upon q to the m minus 1. Actually, if you dabble with it a little bit, it's easy to show that the number is greater than or equal to this. But that this number should be this is a bit of a leap. It's not obvious. And what we actually showed that the splitting subspace conjecture also holds in the affirmative for m equal to 2. Okay. For those of you who know things about finite fields and counting, may recognize this factor q to the m into m minus 1. That is the number of m cross m nilpotent matrices over Fq, the old result of Fine and Hurston. So, in some sense this is like n minus 1 tuples of nilpotent matrices of size m cross m. So, there are bijective questions here. Okay, we did little bit more, maybe I should, we made sort of a pointed version of this splitting subspace conjecture. What is that? It is like topology, you have these pointed spaces and you look at the homology and so on. So, what is a pointed sigma splitting subspace? It is a pair W comma X, where W is a sigma splitting subspace and X is a point of W. Okay, so you fix a point X and that is sort of a base point, and then I have formulated a conjecture which at least in principle looks very, very simple. The conjecture says that you take any X in Fq to the Mn other than 0, okay, and a sigma which generates Fq to the Mn as a field over Fq, then the number of m dimensional pointed splitting subspaces with this base point, fixed base point. So, those sigma splitting subspaces which contains the pre-chosen point X is just this power of Q. Okay. So, this is what I call pointed splitting subspace conjecture. What we showed is that this conjecture and that conjecture are equivalent. I mean, you prove this, that follows and vice versa. And of course, we showed that both of them are true when m equal to 2. So, you could sort of say that this pointed splitting subspaces is equivalent to the assertion that the number of pointed splitting subspaces is like pointed n tuples of m cross m nilpotent matrices. Okay. We did little bit more. Remember, we had this number about the number of primitive vector recurrences, and we showed that in the general case that number is related to this sigma splitting by just this formula, which will explain the quantitative formulation, and that there is an explicit upper bound and there is an explicit lower bound. And if you work this out and cancel some powers of q from both sides, you will see that your lower bound and upper bound have essentially the same order. Well, and then you can actually get a asymptotic formula for the number. For example, for the case of pointed splitting subspaces, you can show that that number is asymptotically equivalent to this. That means as q is large, it is this. And okay, so but all this work had some nice dividend, and this is probably my last slide, which is that two young people, Eric Chen and Dennis Singh, one from I think Princeton and MIT, they looked at, we wrote a sort of expository article saying that here is such a nice conjecture, you do not need to know anything, you just need to know linear algebra and what a finite field is, and you try to prove that, and without any reference to cryptography. And they looked at that and they used techniques from generating functions and so on, and they actually proved that thing. So, they proved the splitting subspace conjecture, and because what Samrit and I had shown, that proves whole lot of other conjectures, because this is the, okay, if you remember the abbreviation, the splitting subspace conjecture is equivalent to the pointed splitting subspace conjecture. Turns out it is equivalent to the irreducible fiber conjecture, which implies the primitive fiber conjecture, and primitive fiber conjecture would imply the block companion Singer cycle conjecture, and that is equivalent to the primitive vector recurrence conjecture. So, if you for example prove this, then everything follows. Okay. And maybe I am running out of time, but there are other more problems and more work in this direction, although this particular problem is solved. For example, you could ask about instead of multiplying by some sigma, you can just take an endomorphism and look at the images and then ask for what is the number of splitting subspaces and things like that. But maybe my time is up, so I think I will stop. Thank you for your attention.